In this module, we will introduce an interesting paradox called Simpson's paradox, which arises when we try to analyze binary data. Historically, the famous example for Simpson's paradox is applied to UCB school admissions at the University of California at Berkeley. Now, there were accusations that there was gender bias in admissions, but later the data was looked at in greater detail and the analysis showed that the conclusions do not necessarily hold and they depend on the methods which we use to analyze the data. In this module, I'm going to choose a similar example which is quite well known. It is taken from the textbook of Agresti and it is to do with the death penalty. I have data on something which is called a 2 by 2 by 2 table, which looks at three variables: whether or not the death penalty was awarded in a particular murder case, the race of the victim, and the race of the person accused or the defendant. The question is whether a black defendant has a greater chance of getting the death penalty, and we shall see in this module that the answer is not necessarily straight-cut and it depends on how you choose to analyze the data. In our introductory module, we had looked at an example on Simpson's paradox. This module is dedicated to Simpson's paradox and we shall revisit the death penalty example which we introduced in the introductory module, as well as look at some other examples and in general the concept of marginal tables and conditional tables and how these might differ. So technically we are considering partial association in stratified 2 by 2 tables. This means that we are no longer considering the simplest example where we are looking at two variables x and y, but we are also looking at a third variable z which we term as a confounder. Confounder is a concept which comes from epidemiology, and the variable z is called a confounder if it is independently associated with both x and y. Thus, age might be a confounder between lung cancer and smoking because we can hypothesize that smoking behavior is related to age and the probability of lung cancer is also related to age. Now note that I have said something about being independently associated with both x and y. This means that the association between z and x and the association between z and y are not necessarily linked, and a violation of this can happen if z is in the causal pathway between x and y. Thus, for example, if we were to say that smoking leads to stress, which leads to high blood pressure, then stress is an intermediate variable between smoking and blood pressure, and it is not considered a confounder. If you are interested in confounders and how we control for them and what happens if we fail to confound for them, then more on this in the modules on biostatistics. For now, we note that in any situation, it is highly unlikely that we would only collect data on two variables, and we are considering analysis in a simple case where we have a third variable which we have termed as z. This variable is called a confounder, and the reason we need to consider this variable is that if we do not, that is, if we fail to control for this variable, then this lack of control may either lead to an association which is spurious or it may mask true association. So here again is the example on death penalty and race of the defendant. This is the kind of 2 by 2 by 2 table I referred to in my earlier slide. So the three variables considered here are firstly death penalty, yes or no. That is, whether or not the death penalty has been awarded in a particular murder case. My other two variables are the race of the victim, which might be white or black, and the race of the defendant or the accused, which again might be white or black. So this is the data on these three variables taken from a set of murders which occurred in Florida, and these have been studied in the Florida Law Review as well as in the book by Agresti. The natural question which arises here is whether defendants of a particular race are more likely to be awarded the death penalty. If indeed this is the case, then it is a very serious situation and that suggests that there is some bias in the judicial system. So let us see what this data has to say about our hypothesis. On this slide, I have disaggregated the data into two partial tables. In the first case, I'm only considering cases where the victim is black. So for cases where the victim is black, we can see that in cases where the defendant is white, none of the cases were awarded the death penalty. In cases where the defendant was black, 2.8% of cases were awarded the death penalty. So in this case, black defendants have a greater chance of being awarded the death penalty. If we look at the second partial table, for the case where the victim is white, we see that if the defendant is white, then in 11% of the cases the death penalty was awarded, whereas if the defendant is black, then in 22.9% of the cases the death penalty was awarded. So again, when the victim is white, the death penalty is awarded more to black victims than to black defendants than to white defendants. So to sum up, for the case when the victim is black defendants are more likely to be awarded the death penalty, and for the case where the victims are white, again black defendants are more likely to be awarded the death penalty. On this slide, I'm looking at the marginal table where I have collapsed across victims' race. When I aggregate the data, I see that considering the total situation, in cases where the defendant was white, the death penalty was awarded in 11% of the cases, and in situations where the defendant was black, the death penalty was awarded in 7.9% of the cases. So this suggests that white defendants are more likely to be awarded the death penalty than black defendants. So we get a set of contradictory conclusions. If we ignore the victim's race, which is what I have done on my second slide, where I have collapsed across race and not taken it into account in my analysis, then my conclusion is that the death penalty is imposed more often on whites than on blacks. If I control for victim's race, which is what I have done in my partial tables where I have disaggregated the data by the race of the victim, then my conclusion is that the death penalty is imposed more often on blacks than on whites. So these two are contradictory conclusions, and indeed it is this contradictory set of conclusions which we call Simpson's paradox. What is the reason for this contradiction? The reason is that my third variable, which is victim's race, acts as a confounder in this example. By this I mean that it is very strongly associated with the two variables about which I am interested in inferring, which is race of the defendant and the death penalty. Indeed, if we calculate the odds ratio for the race of the victim and the race of the defendant, we get a staggeringly high value of 87. Agresti has further tried to explain this diagrammatically in his book on categorical data analysis. So on the x-axis, I have 2 points, 2 locations, depending on the race of the defendant. On the y-axis, I have plotted the proportion receiving the death penalty. For each of the points, I have enclosed it in a circle which is proportional to the frequency of that particular cell in the table. So if we look at the conditional association for the case where the victim was white, we compare the 2 points marked by W, and we conclude that black defendants are more likely to be awarded the death penalty. So looking in this direction, the association we can say is positive. Similarly, if we look at the conditional association when the victim was black, then we connect these 2 points, and again the association we can say is in the same positive direction. However, when we aggregate these two tables, as a result of the change in the marginal frequencies, the fact that this cell has a huge frequency and this cell has a very small frequency, when we aggregate this, the centroids get shifted so that we are looking at a vector which is in the opposite negative direction, and we conclude that the association is negative. This is a diagrammatic explanation of Simpson's paradox. So again, to recall, this phenomenon is called Simpson's paradox. The definition of Simpson's paradox is that conditional associations and marginal associations are in opposite directions. In this case, we have seen Simpson's paradox applied to the case of 3 binary variables, but more generally, Simpson's paradox can apply for any kind of variables, and in particular to the case where we have quantitative variables. The reason why such a paradox occurs is that we have a third variable which we are not really interested in per se, but which can affect our conclusions by being highly correlated with each of the 2 variables in which we are interested. We can define several kinds of odds ratios. So here I have defined the conditional odds ratio. The idea is that we have x, y, and z, where our main variables of interest are x and y, but we also measure z because it is a confounder. So conditional on z, taking the value k, the conditional odds ratio is given by theta xy k equal to mu11k, mu22k by mu12k, mu21k, where mu ijk is the probability of an observation lying in cell I for x, j for y, and k for z. I am not restricting myself to the case of 2 by 2 by 2 tables, but considering general categorical data when each of x, y, z can lie in any number of categories. Similarly, I can define the marginal odds ratio. So the marginal odds ratio for theta xy is mu11 plus mu22 plus by mu12 plus mu21 plus. The plus indicates that we have summed the probabilities over all levels of z. We can try and explain the death penalty example looking at conditional and marginal associations. So for white victims, the partial OR is 0.43. For black victims, the partial OR is 0. However, if we look at the marginal OR, then the marginal OR is 1.45, which is on the other side of 1, and hence the conflicting conclusions. A very famous example on Simpson's paradox is the case of gender bias in graduate school admissions. So this is data taken from the University of California at Berkeley, and there was some suspicion that there was discrimination among women when considering admissions to graduate school. Further analysis of the data showed that there was a third variable which was confounding this association, and this was the department to which the candidate applied. It turned out that women tended to apply to more competitive departments, and it is this competition and not the gender which led to women being accepted less than men at UC Berkeley. Thus, failure to account for department would lead to erroneous conclusions about there being gender bias. Going a step further, we can introduce the concept of conditional independence. So again, I have three variables x, y, z, where each of them can take the value of any number of categories. So x and y would be said to be independent, conditional on z being equal to k if the first equation given on this slide holds, which is probability of y equal to j given that x equal to I and z equal to k is equal to probability y equal to j given z equal to k for all ij. So x equal to I drops out of the equation because x does not give any additional information once we know about z. So in terms of the pi, this is pi ijk equal to pi I plus k into pi plus jk by pi plus plus k for all ijk, where the pluses indicate that I have summed over the corresponding variable. I can also introduce the concept of marginal independence, which says that pi ijk is equal to pi I plus k into pi plus jk by pi plus plus k for all ijk. Now note that if I have conditional independence, then this is the condition which holds. This is the condition which holds for all ijk, and if I sum this equation over k, then it leads to an equation like this, which says that pi ij plus is summed over k pi I plus k pi plus jk by pi plus plus k. Now this does not look like the same as marginal independence, and hence we come to the conclusion that conditional independence need not imply marginal independence and vice versa. To summarize, in this module we looked at Simpson's paradox, which arises when we analyze binary data. Specifically, it arises when we try to look at an association in the presence of a third variable, which we call the confounder. We have considered the motivating example, which was the UCB college admissions. We have looked at this data, and we have also looked at another data set in greater detail, which is the data on death penalty. We have seen that conclusions as to whether or not black victims tend to get awarded the death penalty more depends on whether we look at conditional or marginal associations. We have defined both the conditional and the marginal association, and we have also defined the concepts of conditional and marginal independence and seen that one does not necessarily need the other. So these provide new concepts which you have not used in your earlier papers on regression and are additional problems which an analyst must tackle before analyzing binary data.